encoding language for a neural network. Neural networks cannot be interpret words. If you are sending deep, can't able to send first of all. Here also not available output. So neural networks cannot interpret words still now. Still nowadays, still up to date. Neural network require numerical inputs. Encoding language for a neural network. That's why we are our research going on under encoding language for neural network. So embedding transform indexes into a vector of fixed size. Transform indexes into a vector of fixed size. Vocabulary, corpus of words. This, my, a, cat, took, I, for, walk, morning. For a, indexing, word to index. A means 1. A for 1. Cat for 2. Walk for caption. 1 hot embedding for cat. Ith index. This is embedding index to fixed size vector. Land embedding. Run, walk, dog, cat, happy, sad, day, sun. Handle variable sequence lengths. The food was great versus we visited a restaurant for lunch versus we were hungry but cleaned the house before eating. This is the handle variable sequence lengths. Model long-term dependencies. Model long-term dependencies. We are going to long-term dependencies to be made as model. Here that is sequence length variable handled like this, great, lunch, eating like this. Here model long-term dependencies. France is where I grew up, but I now live in Boston. I speak fluent. What? Model long-term dependencies. Here mentioning like this, we need information from the distant past to accurately predict the correct word. We need information from the distinct past. What happened? Accurately, we need the information. Predict the correct word. Here, what we can say English. Here, what predict? We have to be predict. Capture differences in sequence order. The food was good to capture differences in sequence order. We have to capture sequence in the sequence order differences. We have to capture. The food was good, not bad at all. The food was bad, not good at all. So what we get differences? Here good food. Here the food was bad, but not bad at all. Sometimes good. Here the food was bad, not good at all. Not both are same. Capture differences in sequence order. So we are captured here. Not all the time good, not all the time bad. This is the sequence here. sequence modeling design criteria. To model sequences, we need to handle variable length sequences, track long-term dependencies, maintain information about order, share parameters across the sequence. Sequence modeling, we are going to modeling for what? Sequence, for sequences. That design criteria. What is the design criteria? The model sequence we need. What is the need? That 4 points. What? Variable length sequences to be handled. Long term dependence we have to be tracked. Information about order to be maintained. Okay. Across the sequence we have to be share the parameters. We have to share the parameters. Recurrent neural networks RNNs meet this sequence modeling design criteria. This RNN to be meet this sequence criteria. First, variable length sequence to be handled. Second one is long-term dependence to be tracked. Third one, maintain information about order. Fourth one, across the sequence to be share the parameters. Back propagation through time. Back propagation through time. PPTT. Recall to be remember. Back propagation in feed forward models. Back propagation in feed forward models. Forward this direction, back propagation this direction. So here we have to be in this feed forward models. We have to be apply this one, back propagation. How? We will see. Then, yeah. This one black up direction, red down direction. This one input vector, this one output vector, output hide layer. Black, where is that black? All are here red only. So red only down direction. We see here what mentioned. Back propagation algorithm 2 points. What is this? Take the derivative gradient. Gradient we have already seen. Weight to be partially differentiate with respect to other weights to be loop, to be iteration till get the result. That one is the gradient. So take the derivative gradient of the loss with respect to each parameter. Take that derivative, yeah, they told no partial. I have told partial derivative, but they told derivative gradient of the loss. Loss means here weight here in this hidden layer. Yeah, we can say weight. Why we are going to differentiate for loss purpose only, for reducing loss purpose only. We have to reduce the loss with respect to each parameter, with respect to all the parameter. Shift. That's why first we have to do be partial differentiation. Dou say omega, sorry, w divided by dou w, we can say here 1. total loss. Shift parameters in order to minimize loss. To be shift the parameters in order to minimize the loss. To be reduce the loss, shift the parameters. This is the algorithm for back propagation feed forward models. We will see in more slide, feature slide in detail. RNN, always to be keep in mind. RNN always recurrent neural networks. RNN, recurrent physical meaning. What is this? In neural network, it will be recurrent, recurrent. Okay, recurrent. Okay, RNNs, back propagation through time. What? RNN, X of t input vector, Y capital T output vector, X naught, these are input, these are same weight, this one also same weight, here also same weight in the hidden layer, so not here. Here, this is the hidden layer. Normally, yeah. This is x1, x0, input x0, output y0 vector, loss L0. Here x1, we are getting loss L1, here L0. In x2, loss, after this guiding, here one weightage, here one weightage, here one weightage. Weightage means in between this weightage, in between this weight. Here this is only reducing the loss. We have to differentiate this weightage for loss with respect to here differentiate according to this. Back propagation means this way. This is depends upon this. This is depends upon this. This is depends upon this. That is y2 cap depends upon why. This why depends upon wh. This wh depends upon whx. Like this we have to differentiate. This is that's why we are doing back propagation for loss reducing purpose. All the node up from x0 to xt. So doing so on like same. So total loss we are coming. Okay. RNN, back propagation through time. Forward passing, backward passing. This black color forward, red color backward. What I told you, no? This one. Weight or weight loss reducing. Loss to be error to be reduced. That's why back pressure. This is actually forward. Loss to be reduced back propagation due by using gradient. Standard RNN gradient flow. Standard RNN gradient flow. X dot, x1, x2 up to xt, these are input vector. H0 to ht is the hide vector, hide layer. So this is the weight in between x and h. Here, this node in between this top. Strengthen. In mathematically, we can say